Thank you.
Get better. Okay, so the dry lab normally scheduled for today, that I did not do the schedule, by the way, is dry lab 6. And so click on the assignment for dry lab 6 and turn in the handout that I'm going to give you, okay? All right.
Oh, it says dry lab 6. Yeah. We're just changing that.
Okay. There are various types of reactions. There are synthesis reactions. That means 2 or more things are coming together. And decomposition, which means something is breaking apart. And there are single replacement and double replacement. Single replacement reactions have a metal and a salt. And if the reaction goes, the metal becomes an ion and the salt becomes a metal. Now we're going to go over this in detail today. Double replacement, there's no metal involved. It's just salt and salt. When you mix them 2 together, sometimes a reaction happens, sometimes not. Now that's next week's lab. So next Friday, I'm going to lecture on double replacement reactions. It's like I'm doing here, so you'll know that going into the lab. Okay, most people really like these 2 labs. Their color changes, they're quick, the write-ups are pretty straightforward. They're very popular in terms of this is what chemistry is all about. Color changes and this and that. You know? All right, so let's talk about single replacement reactions. All right, single replacement reactions involve something called oxidation and reduction. Okay. Oxidation and reduction frequently is abbreviated redox. The re is for reduction, the OX is for oxidation. Now, in this reaction, electrons are being transferred, moved around from one to the other, usually from the metal to the salt. So if we look at, let me clear this up here. Let's look at this reaction here. We have copper metal and silver nitrate. Okay, so this is a single replacement because there's a metal and a salt. The salt is the silver nitrate. The metal obviously is copper. So the question is, will that reaction happen? Okay, so let's look at the details of what's really going on there. So we have copper metal. That's what the little superscript 0 stands for. And what's happening there is that copper could lose 2 electrons. So the copper goes from a metal to a salt. Now, when I say salt, that's ionic. What about the silver? The silver is going to go from +1 it's going to absorb an electron. Now, in oxidation reduction reactions, one gives up, the other receives. No exceptions. Because you can't just have these electrons moving around freely. That's called a free radical, extremely unstable. Because they want to become part of something else, more stable. Okay, so the question is, which wants to become more stable? Okay, so we have copper is losing electrons. That means that's undergoing oxidation. The silver is gaining an electron, so that's undergoing reduction. So that's receives electrons. Now the problem is, well, can anyone see the one problem with what I've written down here? Say again?
There's an additional electron offer that it can necessarily you can't make it ionic.
Yeah, we have a problem with the number of electrons being moved or transferred. They've got to be equal. So what must we do to make this bottom equation equal the top one in terms of a number of electrons? Hmm? Yeah, balance it. Now we have 2 electrons transferred, 2 electrons received. Now it's balanced. So let's algebraically add this up. By the way, these are called half reactions. 2 halves make a whole. Okay, we have to have 2 half reactions that are doing the opposite though. So the electrons can go where they need to go. Okay. All right, and remember we have silver nitrate, not just plain old silver ion. So there's a nitrate here that's called a spectator ion. Spectator ions do nothing. Just like at a ball game, spectators watch, they don't participate. And that in this case is going to be the nitrate ion. Okay, so let's algebraically add these 2 half reactions together. So the electrons cancel because they're equal now. So we've got copper metal plus 2 silver ions gives us copper plus 2 plus silver metal. And then we've got the spectator ion here and here. So, question is, will this reaction go? Or will nothing happen? Now, to figure that out, we need something called a activity series. And that'll say whether it's not very noisy out there, just prop it open.
Oh, pop it up.
When it gets noisy, feel free to shut it. Okay, so what does the metal reactivity series tell you? It tells you and these are all metals being oxidized. So this is an oxidation series. Because we're losing electrons here. Okay, what this series says is the higher in the column, the more likely an oxidation will occur. Higher means it's going to occur, lower means it's not. So this says lithium is very likely going to oxidize because it's at the very top. For Goldsmith, this is a good deal because gold is at the bottom. It doesn't want to be oxidized. Okay, so to figure out, and the weird one here is this one here. This has to do with acids. In other words, if you drop copper metal into an acid, what will happen? Versus lead. This will tell you what will happen by the reactivity series. Okay, so we have silver, and we have copper. So, which is the metal we start with on this reaction? Copper metal. So the question is copper metal higher than silver ion? Yes. That means a reaction will go. In other words, copper wants to be oxidized more than silver. But the copper is not oxidized yet until we put it in the solution. Then it'll oxidize, and when it oxidizes, the opposite occurs to the silver, which is what? Opposite of oxidation is reduction. These always go together, oxidation, reduction. So that means the silver metal is going to be reduced. So in other words, this reaction here is going to be reversed. And that's what we have over here. So the copper metal is above the silver. That means it wants to be oxidized more than the silver. So it happens. So this reaction, the way it's written, is going to work. So that copper is going to go away, and all of a sudden silver is going to be there. Now I'm going to do this reaction in lab today as a demo. It's a very cool reaction. I'm going to have a coiled copper wire in silver nitrate solution. What's going to happen is the copper is going to go to the ion, copper +2, which is going to turn the water, the liquid in there, blue, and silver is going to plate out onto the copper wire. It's really a cool reaction. It happens fairly fast too. Okay, so what's important to remember here is the metal higher than the salt. That's the key question. If it is, a reaction goes, and write it out and balance it and do all that cool stuff. If it's not, there's no reaction there, NR. Okay, so any questions about this? All right, let's do more. Now you're gonna have to be balancing equations with a write-up. So the first thing is you write it out and ask yourself, is the metal above the salt? If it is, then you're gonna have a reaction. If it isn't, it's gonna be no reaction. All right, so let's take aluminum, metal, and let's throw it in some acid. Sulfuric acid. Okay. So is this reaction going to happen? Is the aluminum above the H2? Now, whenever we have acids, we have H2. Okay. So in the reactive series, we have to find H2. Okay, so here's H2 here. And aluminum up there. So is aluminum above the H2? Way above, all right? Now, the farther it is away, the faster the reaction will go. Closer they are together, it'll be slow, but it will happen. Okay, so now we have to balance this thing. Now, so we have H2 hydrogen gas gives off 2 H pluses and 2 electrons. So aluminum does that. And then our does that. Okay, if we algebraically add these up together, the electrons don't jump. So remember when we were balancing equations, when we had a 2 and a 3, we had a common denominator of 6. Do the same thing with this. So we're going to make this out so there's 6 electrons. Okay, so to make 6 electrons, we're going to double the top one. And triple the bottom one. Now, 6 and 6 electrons. Now it'll balance out now. So we've got what's the spectator ion? What didn't we use? SO4. Now, in both single and double replacement reactions, you're going to have spectator ions. Whenever we have a salt, we have a cation and an anion, positive and negative. one of them will participate in the reaction, the other will just tag along. The one that tags along is a spectator.
Why is that a Peter negative two?
Because this is an acid. And you can go on the side here. If you look up SO4 in your ion chart, it's going to be -2.
Okay.
And if you look up hydrogen, when it's an acid, it's a +1. So that means we need 2 + 1 to balance the -2. So H's are positive when it's an acid. If it's not an acid, they're -1. Hydrogens are weird because they have one electron and they can go either way. Sometimes in the periodic table, they'll put 2 hydrogens up there, one on the far left and the other one next to helium, because it acts like both of them. Okay, so what do we got here? And because aluminum is way above H2 on the reactivity chart, it's going to happen. Now, the problem sometimes is we're working on a very small spot plate. Spot plate is about that big around, and we're going to do all the reactions on the spot plate. Some of these reactions happen, but you just can't see it happen. So there's no visible reaction, NVR. So keep that in mind when you're doing these reactions. You're going to predict, then you're going to do it on a spot plate. And then you say whether your prediction is right. But keep in mind that sometimes reactions happen that you can't see. Another example is when you do a neutralization reaction. A neutralization reaction is an acid plus a base makes something called water. But you can't feel it, and it gets very hot. Well, the reaction space is so small, you can't tell if anything happened. In other words, it didn't get hot. It did get hot, you just can't feel it. So if you had a super sensitive thermometer, it would register positive. But we don't have super sensitive thermometers in lab. So we can predict it, we just can't show it. Okay, now these are a matter of, now sometimes they want you to balance it with the spectator ion. So the spectator ion was up here with the acid, and we tripled that. So that means we would need to have oops, excuse me, put it on the wrong side. So that way we accounted for everything. Okay, but this is the meat. Spectators don't do anything. Okay, so the tricky one is going to be with the acid, the H2SO4, the HCl. So we have H2SO4, hydrochloric acid. What else do we need here? Nitric acid. Those are the three strong acids you need to know. So whenever we have any of those acids in play, we're going to be using this guy here. All right, so let's do, okay, this is the procedure for today's lab. You're gonna have two demos. I'm gonna be doing them up front. And then you're gonna react various metals with hydrochloric acid. And the next one down, part D, is we're going to be taking copper and these salts. Now, you'll notice sulfuric acid is in there, H2SO4. Now, it says to give 15 minutes for the reaction to happen. Some of them it'll happen like that. Others will take a while. Now, how do you know a reaction occurs? Change in color, bubbles, hot or cold. Now, the problem with hot or cold, you're not going to be able to test that. You're going to predict it, but you can't test it. The others should be observable, though. Whether you see bubbles or not, whether it turns gray, the color of the solution changes color, all those are indicators that a reaction has happened. Okay, and that's the essence of this lab today. Goes fairly fast. What takes the longest part is producing the equations. And it's best if you do them in lab. You can ask questions. Now, you may do the questions at home like we normally do, or you can stick around. Now, you also have this handout for lab. Last semester's test 2. Okay, so let's do some more of these. Okay, so let's choose a metal. Let's choose a zinc. Zinc metal. And some solution. And let's do sodium sulfate. Now I had to put a 2 there because sodium is a +1, sulfate is a -2. That's why we need 2 pluses to balance the -2. Okay, so metal salt. Okay, metal salt, that means that's a single replacement reaction. So we need to look at the okay, so here's sodium. It's pretty high up there. And what was the other one? It was zinc. Where's zinc? Okay, so is this reaction going to go?
Yeah.
Why? That's correct. The metal is under the sodium. So this is a NR, no reaction. Yeah, again, that crucial question, is the metal above the salt? If it is, it'll go. If it isn't, it won't. And again, the further they're apart, the faster and more vigorous the reaction will be. If they're really close together, it's going to be a slow reaction. Still go though, but it'll be slow. Okay, and that's what you need to know about single replacement reactions. It involves metal plus salt. If you have two salts, let me give an example of a non-single replacement reaction. So this would be no visible reaction. That's the prediction. And then you check it out and see if it happens. Okay, so this is a single metal plus salt. Let me show you an example of a double replacement. That's salt and salt. So we take, for example, now, sodium is a metal, silver is a metal, but it's in its salt form. So this is a +1. This is a +1. So this is a double replacement reaction. So there's a different set of actions you have to go through to work with a double replacement reaction, which we're doing next Friday, to go with your lab double replacement. So next week is going to be a dry lab and wet lab as well, because the wet reactions, the wet labs are pretty short. So are there any questions about single? Yeah.
If sodium's above aluminum, why does it react sodium flux?
The question is, aluminum hydroxide is more stable than aluminum metal. It's all stability. Everything in the universe is a stability. Now, the only clincher in that is entropy, which can reverse that, by the way. So an entropy is a measurement of organization or randomness. So the more random it is, that's positive entropy. And that's a function of temperature also, which can overcome the other one. But normally, unstable to stable. That's what happens. Okay, so let's do another couple examples of single replacement here. Let's stick with zinc. And let's add in need a salt here. Now I'm going to introduce another topic here that's going to go with next week and this week, something called aqueous. Aqueous means it's a salt. Correct. Well, acids are also aqueous. Okay. That means the ferric oxide ferrous oxide is dissolved in water. Okay, so we put these two together. We got a piece of zinc metal, we throw it in the ferric oxide solution. What's going to happen? Okay, which is the metal? Zinc. So if zinc is higher on the reactivity chart than iron, it'll go. We have zinc and iron. So zinc metal is higher than the iron. So that means that reaction is going to go. And you'll notice, pay attention to the charges also. Notice it's iron +2 or iron 2, and it'll go to, the zinc is going to be a +2 also. Okay, so the zinc is going to lose 2 electrons. And the iron is going to gain those 2 electrons. So on the left, it's gaining, on the right, it's losing. So this is nice because it already worked out. 2 electrons lost, 2 electrons gained. So we don't have to fuss with multiplying them by anything. So we're going to have, so the electrons cancel. So we have iron +2 plus zinc metal is this iron metal plus zinc ion. What's the spectator? Oxygen. So an ion of oxygen is called oxide. So the oxide spectator. Again, if the metal is higher than the salt, it goes. That's the single most question. So if I ask you why on your tests, now this test 2 has got a single replacement reaction in it. It's got a double replacement reaction in it. So I'm also going to put out a key as well. I'll post that as well. Were you going to remind me?
Yeah.
Yeah, remind me to post a key also. Okay, so that's it on single replacement reactions. Straightforward. All right. Why don't we end here? And I'm going to pass out this handout, and you can start working on it. Okay. And then we get over to the lab, you'll have at least started on it.